Okay, well, it is 10:02, so I think we'll go ahead and get started. My name is Dan Pro. This is Neometrics Technologies, and today's webinar is on applications for metal 3D printing. Our presenter this morning will be Kelsey Noyes, who joined us earlier this year to help promote our sales of Markforged 3D printers. I would like to invite people, as the presentation proceeds, to go ahead and put any questions that you may have into the chat box. We will try to address those in between slides. If any questions that we don't get to during the presentation, we will be glad to answer at the end of the last slide. So without any more ado, I will hand the floor over to Kelsey. And Kelsey, please take it away.
Sounds great, thanks. Well, again, welcome everyone. I'm glad you're able to join us today. Here's our agenda. It should take about 20-25 minutes. And I'd like to start by introducing you to Neometrics. Then we'll take a look at the available metal 3D printing technologies available today. And then specifically, we'll look at the Markforged 3D metal printing process. And we'll see the available metal materials. And finally, I'd like to share some customer success stories. All right, Neometrics has been delivering 3D engineering solutions since about 2003. We provide services for scanning, if you have a reverse engineering project or inspection. We also have a number of 3D printers in-house available to print parts for customers. We sell equipment for 3D scanning and 3D printing solutions, as well as any related software. We provide complete training on all hardware and software solutions. And today's webinar will focus specifically on the Markforged metal 3D printing solution. There are a variety of metal 3D printing methods, and today we'll briefly review 4 common methods: powder bed fusion, binder jetting, direct energy deposition, and metal extrusion. Do any of you have experience with these methods currently, or are using any of these solutions? Feel free to add comments in the chat. All right, powder bed fusion starts with loose metal powder and then fuses the particles together by a sintering or melting process. Sintering uses a combination of heat and pressure to get the particles to stick together. Melting uses a high enough heat so particles actually fully melt together to join and create a solid part. Fun fact is the first 3D metal printing patent was for DMLS, or direct metal laser sintering, in the 90s. Overall, powder bed fusion can use a wide variety of materials. Nearly any geometry can be formed. But due to the powder, the surface finish is similar to a sand-casted part. And because of the metal powders itself, it can be dangerous and requires strict process controls. There's a high cost with this method due to materials, machinery, and operation. The binder jetting process also uses metal powders, but instead of fusing the particles with a heat source, a liquid binding agent or glue is used. It can quickly print a part layer because it uses multiple print heads. It operates at room temperature, so there's no heating during the print. Later, the parts are sintered in an oven. It's a good large volume printer. It's able to quickly print many parts. Again, due to the dangers of loose metal powders, extra care must be taken for safety. There is a high cost for proper facility requirements, machine, materials, and operation. All right, direct energy deposition. This is a unique process where the metal powder is pushed through a nozzle and then immediately melted by a heat source, typically a laser, but it could also be an electron beam. It's actually very similar to welding, so a typical application would be repairs on large parts like turbines. It's usually mounted to the end of a robotic arm. It's great for producing large, simple shapes, but not for small parts or tiny details. Parts produced with direct energy deposition tend to have low resolution and a rough surface finish. The cost is also quite high for the machine and operation. All right, metal extrusion. This technology uses the FDM or FFF 3D printing process. Metal powder is encased inside of a plastic tube and then extruded through a heated nozzle. Using this enclosed filament makes it the safest 3D metal printing option. It's extremely easy, office safe, and the most affordable method available. Atomic diffusion additive manufacturing, or ADAM, is a proprietary 3D printing process developed by Markforged. It's an end-to-end process that starts with metal powder completely wrapped in a wax and polymer binder, which makes it very safe to handle, and then it's loaded into the Metal X printer to print the part one layer at a time. The printed part is a green part, then it goes through a wash process and called a brown part. Finally, it's sintered to become a completed metal part. We'll walk through all of the stages from initial design to the completed part. It all starts with a CAD file. All you need is an STL file that you import into Eiger, which is Markforged's cloud-based slicing software. Files can be easily accessed to anyone in the network, so parts can be sent to printers globally. This enables a digital inventory. Parts can be printed when and where they're needed. When Eiger slices the part, it gets scaled up to account for shrinking and deformation in the downstream processes. Eiger then slices your part into discrete layers and identifies overhanging features, builds supports, and a raft underneath your part. All right, so here's the printing process. The spools are shown on the picture on the right. There's the stainless steel metal on the left. And remember, that's the metal powder that's wrapped in a wax and polymer. And then on the right, we have a ceramic spool, and that's used for release layers and for easy removal of supports. When a metal part prints, it prints on a raft, typically with support structures. The raft provides a good base for the part, preventing warping and ensuring standard shrinking in the center. In the wash, the first stage of the binding material is removed. The green part is taken from the printer and placed into the wash basket, which is then lowered into the solvent. The solvent dissolves most of the binder material. After washing, it's in the brown part form. It's more fragile than a green part, but still bound together. Sintering transforms a brown part into a fully metal part. To do this, the temperature is ramped up slowly to burn away the trace amounts of remaining binder material. As the temperature ramps up closer to the melting point of the material, the metal particles fuse together to create a strong metal part. The part is heated from room temperature to about 85% of the metal's melting point, and then it slowly cools down. In the early stages of the temperature ramp, the furnace burns away the remaining binder through the tiny channels created by the washing process. As the temperature reaches its peak, the part actually shrinks to about 17% to its final size, while the ceramic supports turn from filament to dust. The machine then slowly cools until it's safe to remove the part from the furnace. After sintering the part, you can remove it from its support and raft. It's ready for use in a wide variety of applications. You can also post-process the part to improve mechanical properties and surface finish. Metal X printed parts can be post-processed in most of the same ways that a normal metal part can. Heat treatment can improve strength, stiffness, elongation, and hardness. Metal X parts can be surface machined to achieve an impressive surface finish. Sanding or polishing printed metal parts can actually improve the surface quality to a near mirror finish. And to review, these are the steps from beginning to end. It's as easy as design, print, wash, sinter, and then finally use your completed metal part. You may be wondering which metals are available to use in the Metal-X system. We'll now review the metal filament options. Which metals do you guys prefer working with? Again, feel free to make comments in the chat and let us know. (17.4) stainless steel is a very popular choice because it can be used for a wide range of applications. It's a strong, hard metal. It resists corrosion. It can be heat treated as well to increase the hardness if necessary, which brings it to 95% wrought steel strength, which is quite impressive. Copper is a great material that can be used where thermal or electrical conductivity is required. Some companies have worked with aluminum over copper because of traditional processing challenges. Now, those same companies can take advantage of easily 3D printing a copper part and benefit from the material's higher thermal and electrical conductivity. The chart illustrates common metals conductivity, and it's clear that copper is the best option. Inconel 625 is a unique superalloy. It's extremely corrosion resistant and strong at very high temperatures. It's great for printing functional prototypes or end-use parts designed specifically for harsh environments. H13 tool steel maintains a high strength even when subjected to extreme temperatures. A unique application is injection molds. H13 can be used to print molds with integrated cooling channels, which offer more uniform cooling. It draws heat away from the mold cavity. The ability to produce injection molds like this can give manufacturers the ability to reduce part warping, increase throughput, and lower operational costs. All right, and then we have A2 and D2 steels. These are cold work steels defined by their extremely high hardness after heat treatment. A2 is an air hardening cold work steel. It's a 5% chromium steel which provides high hardness after heat treatment, and it has great dimensional stability. D2 offers excellent wear resistance. It's widely used in applications that require high compression strength, sharp edges, and abrasion resistance. All right, so now I would like to share a few interesting success stories. A company in Germany, PTZ, they use a tool cooler to engage and disengage a cutting tool in the shank of an end mill through thermal expansion and contraction. The more conductive the cooler, the faster they could reconfigure the tool. Their original tool cooler was made with machined aluminum. It was simple to produce, but it took a long time to heat and cool, so it created a much longer cycle time than they desired. So they decided to 3D print the part in copper, and this was the perfect solution to the problem. The new design featured conformal cooling channels, which made the tool cooler extremely efficient. This design was impossible to manufacture using traditional methods. The new copper design is 38% faster at cooling than previous designs. They saved 111 hours per year by eliminating about 40 tool changes per year. And this means a savings of about $7,000 a year in machine time alone. All right, the next one is a company called Shukla Medical, and they produce tools for orthopedic surgeons. Specifically, they design tools for orthopedic implant removal. They take out old, ineffective implants before replacing them with new ones. These tools can be quite complex, but Schukel is known for their simple, intuitive designs. Helicopter sockets are used to completely remove screws while keeping bones intact. They wanted to create various prototypes to put in surgeons' hands to test form and fit. They were able to print initial prototypes quickly with onyx, and then they moved on to stainless steel for their final prototypes. Having the printers on site saved them a lot of time and money. And then our final application is a unique story, RPG Industries.
When we were introduced to the Metal X, we were blown away. We saw the possibilities. We can cut delivery times down considerably. We were able to print overnight, lights out, without any human intervention other than getting the printer started. It greatly saved time, and time is money. We have a customer, D&D Automobile Restoration. They had a part from a classic car that they're restoring that is no longer available.
The part they're making for us now is for a Solex carburetor. It's a part we cannot find anywhere in the world at the present time.
This is a one-of-a-kind part, the perfect use for the Metal X.
We were desperate, and they approached us about this new technology that they had just acquired.
They were excited. They were getting very frustrated. We took the part from them, we scanned it, we created a model.
RPG printed a part in onyx for us as a trial run. We fit that to the carburetor, and it fits perfectly.
They were able to tap the holes in the onyx, test fit it, make sure that everything would work, and then we went ahead and committed to printing it on the Metal X. If you were to try to machine this part from scratch, it would be cost prohibitive.
So it's wonderful.
Composite and metal printing are really going to be the future in our industry, and we want to be the early adopters and the experts in that area before it becomes mainstream.
They ended up then taking that CAD file. They wanted to make prototypes initially in onyx. Once they found that they had a perfect fit in onyx, they went ahead and actually 3D printed a stainless steel part, and it fit perfectly. The car was able to run. They were really happy. So I think this is a great example of, if you have a part that no longer exists, you can actually create it in 3D metal printing. All right, and that brings us to the end of our presentation today. If you have any questions, please feel free to chat. If you had any specific applications you'd like us to look at your part, we encourage you to send us a CAD file. We'd be more than happy to look at that. If you have any service work that you need, or if you just want to discuss, what is the best material, we're happy to assist.
Okay, we did have a couple of comments come through in the chat. Somebody had asked about 1018 carbon steel or 304 stainless steel. So neither one of those materials is currently available on Markforged. Probably the closest option would be the 174 stainless. But new materials are constantly being developed, and I know that they're looking to be releasing a few different types of material coming out here over the course of the next year. Any other questions? Folks, feel free to put those in the chat. We'll keep the chat box open here for another few minutes. And then if we don't see anything else come through, we will go ahead and wrap up.
Yep, thanks again for attending. I hope everybody enjoys the rest of their week.
So I think Kelsey did mention that we do offer 3D printing services. So in case you didn't pick up on that throughout the presentation, Neometrix is a reseller for Markforged, so we do sell these printers. In addition to the metal, we also have the composite printers available. So if you need, let's say, the strength of aluminum, but if you're not really looking to invest in a metal 3D printer, the Markforged composite machines, which offer carbon fiber reinforced nylon, would be a very good substitution option for aluminum parts. So as opposed to waiting for a machine shop to produce parts for you. You can print them, small parts can be done in just a few hours, larger parts, overnight. And then also, in addition to the 3D printing services, we also offer 3D scanning, reverse engineering. So if you had a part that you'd like to print, but you don't have the CAD, we can help with that. Scan the original part, create that 3D CAD model, and then you can either 3D print that directly or go to a machine shop. Anybody who has any interest in any of those options or services or any of the machines we represent, Kelsey has her email address up there on the slide. So Kelsey at neometricstech.com. Go ahead and shoot her an email, and we would be happy to help. So with that, we haven't had any more questions come through, so I think we will go ahead and wrap it up. I would like to thank everybody who took time out of their busy schedules to sit in and watch this presentation for us today. Thank you so much, and hope everyone has a great day.
Sounds good. Thanks.